As we begin exploring exponential functions, we're going to start with graphing them, and we want to graph exponential growth functions, and we want to understand how to graph decay functions. Here's some of our vocabulary that we're going to have to go over. Thankfully, exponential functions should be a review. We covered them in depth in Algebra 1. So understanding that exponential growth is something that is going to enlarge an asymptote is that value that we gradually approach but never touch. Let's see here, exponential decay, of course, decreasing, growth factor, decay factor. We'll see how all of these fly into our equation. So an exponential function is a function that when we see it, it has the variable in the exponent. Okay, so you have a base and then your variable is somewhere in the exponent. So when your base is greater than 1, means it's going to be enlarging, and it would be the exponential growth occurs when the initial amount increases by the same percentage over a given period of time. So if we have 2 to some exponent, and disregard, let's talk about that one right here. So graphing this exponential function, 2 to the x power. So just think about when as they plugged in these values, you're actually going to see the reciprocals occur. So let's see here. We have anything to the 0 power. Think about it. 2 to the 0 power would be 1. 2 to the first power, right? We're plugging that x value in. X is 1 is 2. 2 to the second power is 4. 2 to the third power is 8. Now it works the other way. Remember, when we have negative exponents, 2 to the negative 1 is actually 1 over 2. 2 to the negative second is 1 over 4, and 2, goodness, and 2 to the negative 3 is 1 over 8. So you can see how this, when we talk about exponential functions, how this reciprocal is occurring. See we have 1, and then of course we have 2, 1/2, 4, 1/4, 8, 1/8. So we see this reciprocal effect. And as we graph those points, of course my y-intercept is going to be where x equals 0. That's my y-intercept. So the y-intercept is going to be 1, or 0, 1. The point is 0, 1. And just looking as I graph, x is 1, x is 2, x is 3, and being able to visually see what is going on. The thing that we approach is the asymptote. So the end behavior, as x is approaching negative infinity, what is happening to the y value? The y value keeps getting increasingly close to 0, but never touches 0. There's no value that you can plug into the exponent to make a problem equal 0. The only way you get 0 is if you multiply by 0. So the exponent of 0 is usually a default. People say, oh, exponent of 0. No, exponent of 0 is 1. So with that, just keeping that in mind, that the end behavior as x approaches negative infinity is going to be y equals 0, because that's what y is approaching. And then as x approaches positive infinity, y is also going to positive infinity. So just being able to look at those kind of things. Domain is all real numbers, right? It goes forever and ever in both directions, but my range is going to be all positive real numbers. So anything greater than 0. Okay, so my range is y is greater than 0. Not equal to 0, but greater than 0. So just looking at those characteristics. Let's go back. Now, again, this the growth, that's exponential growth, because what you have here is you technically have this function was f of x equals 1 times 2 raised to the x power. So 2 is a growth. Basically, 2 is 200% growth. Now here, looking at this, so here as we go to graphing these transformations and understand what's going on, this is the basic transformation of most functions, and in this case exponential functions, that your a value, just like when we did quadratics, we had y is equal to I think the vertex form was x minus h squared plus k, and we learned that a makes it, either shrink, compress, however you want to look at it, flatten out or get steeper. We knew that the h moved left and right on the x-axis. We knew that the k moved up and down on the y-axis, and then if the a was negative, it would reverse the function. So here is the same effect. You have your b value, and then a, of course, is the initial. What is the initial? Your x minus h is going to be what's going on in your exponent. So h is going to be how we move left or right, and k is going to be how we move up or down. Same effect, different parent function. So here g of x, so we know that it reflects. Negative 1/2 means that it reflects over the x-axis and compresses vertically, which means compresses vertically. Think about it, as we compress vertically, we get more narrow, so it looks like it is going to go up faster or down faster in this case. Okay, that's what it means, compressing vertically. H is -4, right? This would be x minus a -4. So -4 means that we moved -4 spaces. So somehow we went from the origin to, or think about your origin, 1, 2, 3, 4. Okay, we would have moved -4 spaces. And then 1, we would have moved +1. So we went from 0, asymptote being 0, to the asymptote being 1. Okay, so that's what we're talking about. So we moved it left 4, moved it up 1, being able to understand what those numbers mean. Let's see here, analyzing these graphs. Identify the value of k and write the function for the graph of j of x equals f of x plus k. So we have this j of x function here, and they want to say relates to this function. How did f of x change? Or I'm sorry, f of x is that. How did j of x change? Well, f of x would have been something along the lines of that would have been f of x. And what happened? Well, it looks like my asymptote would have been 0, but now my asymptote is -2, right? We approach but never touch -2. So that tells me that we went down 1, 2. We translated down 2. So that's what we know. We know then that we have -2. So it'd be 3.5 at raised to the x power -2, because the k value, k is equal to -2 because we translated down. So the graph has been translated 2 units down, so k is -2. Let's see here. Exponential growth that can be modeled by this. This is very important. This is on your cheat sheet. When I say your cheat sheet, your state reference sheet, but understanding that exponential growth. So you're looking at, this is that thing that we did a lot in Algebra 1, exponential growth, and this is my growth factor, 1 plus the rate, whatever the rate is, going to be a percentage. And then my initial cost, or initial investment, or initial start, initial value, and then the time, how often it happens. And in this case, this would represent like once a year. So again, the growth factor here is what appears inside your parentheses for the exponent. And understanding that, you say Mr. Lopez recently won the lottery. Supposes he takes the lump sum payment and he invests $50 million into an account that yields 5% interest annually. Graph a function that models that amount of his account, then estimate the amount in the account after 20 years. Okay, again, your initial value, 50 million is what he put in, 50. Your rate was, so 50, your rate was 1 plus 0.05, because 5%, again, 5% is equal to, sorry, that's 50%. 5% is equal to, take the decimal, 2.05. So with that, and put it into the graphing calculator, and as we've done this in the past, if you put it to the graphing calculator, we got y equals, and then you have 50 parentheses 1 plus 0.05. You can just leave it like that, parentheses, and instead of using t, use the variable button, which is xt, theta, and so forth. And then when I put it into the graphing calculator again, this is what it looks like when I input it into the graphing calculator, and then I can turn around and look at my table. But understanding that when I have a variable, I don't use the letter x, I use the variable button right here that has x, t, theta, and n. So that's your variable button. You want to make sure you use that, and it's going to give you your table information. Of course, you can look at your graph and see the graph. So keep that in mind, making sure that we're utilizing this. Again, we do this all the time in this class. We want to make sure that we're doing it right. And then check. And this check, go ahead and take a moment to do this check and then come back and check your answer, pausing the video. But what do we have to do on New Year's Day? Alma begins a saving plan. She saves $1 the first day of January and increases the amount she saves each day by 1%. Find the growth factor, then use a graphing calculator to estimate the amount of money she should save in 180 of her day 180 of her savings plan. So there you go. So again, using the formula, we have the initial amount that she puts in is $1. So we have 1 plus the rate, which is 1%, which is 0.01. How long is it going to be happening over time? Be 180 days. So with that, f of 180 is going to be equal to 5.9958 and a little bit more of a decimal, rounding up to approximately $6 after 180 days. Okay, so that is exponential growth. Now, exponential decay. Exponential decay is going to, instead of looking like this, which is my exponential growth, right? Exponential decay is going to look something like this, because we are taking portions away each time and it is getting incrementally smaller. So with that, exponential decay, that is often referred to, used in bacteria and growth models and those kind of things, populations. And I didn't really specify before, but it was in the examples that when we talk about exponential growth, we're often talking about savings, investments, those kind of things that are compounding. That's usually the examples. But decay is talking about depreciation and often the modeling of populations. So here are uranium and science and those kind of things. So here we talk about exponential decay, and it is decreasing, right? Occurs when the initial amount decreases by the same percentage over a given period of time. Exponential function. It occurs when we're somewhere, my x is a decay factor somewhere between the value of 0 and 1, right? We're taking a portion away. So with that, what does that mean? Think about it this way. If I have $1 and I take half of that dollar away, I have a quarter. If I take half the quarter away, if I take half the dollar, I have 50 cents. And if I take half of 50 cents, I have a quarter. If I take half of a quarter, I have a bit, 12.5 cents. And so forth. As I keep taking a portion away, there's always something left behind. Okay, so that's why we're approaching some asymptote but never touching it. So that's what we're talking about as we decay. Now, if the value of my exponent, if x is equal to 1, then we just have a constant. Okay, so that's why it has to be less than 1 or greater than 1. So here, looking at this, is it growth or decay? That is 500%. You got to think about it. I have, that this would be, this A here would be equivalent to 1 times 5.00x, 500%. This one would be some, 2/7 falls somewhere in between 1 and 0, so that would be a decay. This is actually 1.33 to the x power, so that is growth because it is greater than 1. This is greater than 1, so it is going to be growth also, and this is less than 1 because 0.85 is basically 85% of something, which is often a good way of saying that, hey, when I drive a car off the parking lot, when I buy a car and I drive it away from the dealer, it loses 15% of its value right there. That's what they're talking about. No longer 100%, it's down to 85%. So again, as you graph it, much like we did on the last one, and they created a table of values and looking at the estimates, you can see in the table data when I put this into the graphing calculator is we're way up in positive infinity here, and as we keep coming down and we are approaching, we hit our y-intercept where when x is 0, y would be 1/2, or y would be 1, sorry. When x is 1, y would be 1/2. And then we start getting smaller and smaller. We're getting smaller all the way. As you can see, we're starting off with big numbers, cutting them in half each time. Getting smaller and smaller and smaller and closer to 0, but never touching 0. So that is my asymptote. So as x approaches infinity, positive infinity, it's approaching 0. As x approaches negative infinity, y is continuing to grow to infinity. So looking at those kind of things and being able to do those function comparisons. And here, again, the transformation, the understanding, you know, you have a, b to the x minus h plus k. K moves it up and down. A can flip it. So in this case, it looks like we do have a negative a. Negative 2 is my a value, so it is reflected over the x-axis downward instead of, it's coming from negative infinity instead of positive infinity. H is 4, so we are moving right 4, so we go 1, 2, 3, 4. My values have moved right 4, and then the k value has moved up 3, 1, 2, 3. So now my y-intercept, my apologies, my asymptote is actually the value of y equals 3. So all of these things are being able to identify looking at these functions, the characteristics of it, understanding the definitions so we can identify the characteristics. Comparing exponential functions or comparing functions. Here it looks like they have given us consider these two functions. We have f of x. Here we have and g of x shown on the graph. Okay, so what they did was they took f of x, it looks like a piecewise function, right? For all values, when x is less than -1, we use the exponential function. When all values is x is greater than or equal to -1, we use these linear functions, so they've graphed it here. And what do you see? What are the comparisons? They've drawn some data here. They said, hey, let's look at these numbers and we can come up with some point values for f of x, and then answer the questions. Which function has a lesser relative minimum? This exponential function does not have a relative minimum because it continues approaching 0, but never touches 0. But f of x, though, does have a minimum of y is 2. Okay. And then let's see here. That's about it. Let's see here. Compare the y-intercepts. The y-intercept of f of x is 4. The y-intercept of g of x is 3. So we know that this one has a greater y-intercept. My end behavior for this function as x approaches negative infinity and x approaches positive infinity, y is approaching infinity. Here, as x approaches negative infinity, y is approaching 2, because that's my asymptote, right? And then as x approaches positive infinity this direction, y continues to go up in a positive infinite direction. So that's understanding end behavior. And that's really a lot of the information that we need to get to be able to do our graphing and function comparisons today. So again, being able to model, being able to use your graphic calculator to find your table, using your table to plot points, using those point values, then connecting them, looking and see the transformations, your asymptotes, your y-intercepts, your end behavior. All of that is being used here. When I talk about end behavior, I'm talking about the extrema of minimums. So we're comparing and utilizing all of that in this function, and we can see it in practice.